it's important to understand that bottlenecks can have a great variety of characteristics. For instance, they might be internal or they might be external. We've talked about this before with the Tesla example. Tesla at the moment cannot produce because they don't receive a sufficient amount of parts. Now, that's not always the case. So let me give you one example from a company that I worked for. I worked in the sales engineering department, so we planned automated material flow systems, and we had some good years. The economy was thriving. In fact, it was going nuts at the time. And I had to reject projects quite a bit. So customers called or sent me emails, and I had to tell them, no, we don't have time. We don't have capacity for you. I'm sorry. And in one particular year, I rejected projects worth more than 500 million euros. I think by the end of the year, it was almost 1 billion. And that was because my engineering team didn't have the resources to work on these projects because they were busy with existing projects. Now, at the same time, we spent millions on marketing. Not my team, but the company. We spent millions on marketing. Now, every year we had one of the largest booths at the LogiMAT trade show, which is the largest trade show for intralogistics in the world, and that cost millions. We revamped our marketing completely. We got a new corporate design. We did a lot of marketing films that we put on YouTube and LinkedIn. And I fully understand and appreciate the importance of being adequately represented at LogiMAT and other trade shows. But in times like the ones that I'm citing here, we should have shifted gears, and we should have done a couple of things a bit smaller and spent, not all that money on marketing, because we couldn't serve the customer interest anyway. There's no point in making people hungry if you can't serve them food. And this is bottleneck thinking. This is important to understand. Most people don't think in terms of bottlenecks and thus direct the resources they manage towards the wrong targets. Now, there are many other aspects of bottlenecks that are worth discussing. So one thing we briefly mentioned already is that the capacity of a bottleneck will be limited either by its physical capacity or by organizational rules or operational procedures, operational inefficiency. So this is about the origin of the bottleneck. Where does it come from? Why do we have it? Is it a bottleneck because we simply ran out of resources, or is it a bottleneck because we have stupid rules? And we've got the locus of control. The locus of control is a term that comes from psychology, and it describes to what extent an individual thinks that he or she is able to control the circumstances of their life. And the same thing you could apply to bottlenecks. And you could ask, are we able to change something about this bottleneck, or are we not? So, for instance, at the moment, when the bottleneck is external, many people would be inclined to say, it's an external bottleneck, I can't do anything about it. But then there are some companies who do something about it. So, for instance, one of the critical resources we have in the car industry are semiconductors. And another one is lithium for batteries, especially for electric car makers. And then, of course, you can say, lithium is that the lithium production is the first step in the supply network. It's the first step, because then out of that lithium, that lithium is processed, and then you turn it into batteries, and then those batteries, then they come to your plant, and then you can use the batteries for your cars, which is true. But you could also say, if lithium is such an important resource for us, because we are in the electric car business, we could also try to own a lithium mine. We could also try to go deep into the supply network and do something that we normally don't do. We own or manage or control tiers very deep down. And some companies are doing this. It's very rare. But Tesla, for instance, is doing this. I don't recall what exactly it was which they decided to take control of, but it was one of those critical resources which they need for electric cars. I believe it might have been lithium. Maybe it was semiconductors. I don't remember. Anyway, other companies don't do this. So Tesla has a much, much stronger locus of control. They know if they want, they can change certain things in their favor, whereas many other companies just accept it as, well, higher, as fate, basically. The next question to ask is the bottleneck intended or is it not intended? Is it planned or is it unplanned? Now, one thing you have to realize is that every system has a bottleneck. Every system has a bottleneck. So that means you can as well plan the bottleneck to be in a particular location. You don't have to guess where the bottleneck is or let it emerge unplanned, because then you're in trouble and you have to work around some unforeseen situation. So that is something. And very often when you plan a system, you want a conscious decision about where the bottleneck is. But I can guarantee you almost nobody does that. The next thing is it necessary to have the bottleneck in a particular place or not? Is the bottleneck avoidable or is it unavoidable? And this question is related to the origin of the bottleneck. It's also related to the locus of control. It's therefore also related to the location of the bottleneck. So these different factors that you see here, these different aspects that you see here, they are not quite independent as they should be in a morphological box. But you still get the point. Then we talk about the duration of the bottleneck. How long is the bottleneck going to be there? Is it a short-term bottleneck? Is it a medium-term or long-term bottleneck? Is the bottleneck going to stay there? Or is it just a bottleneck that just briefly emerged and then will disappear again in no time? In which case we may not have to do anything about it because we have sufficient inventory buffers. The appearance of a bottleneck is not the same thing as the duration. Is it short cycled, mid cycles, long cycles? How long in advance do we know that the bottleneck is about to emerge in a particular location? Is it something that will happen very, instantaneously? So let's say today we have a couple of companies that do not receive sufficient supply because there are idiots with rockets in the Red Sea, and so the supply route is disrupted. Now, this could not be foreseen, at least not the exact point in time when it happened. But there are other developments in society where we know we're going to run into trouble. For instance, the lack of labor. And the lack of labor, you can also not foresee when exactly it's going to hit you, but you already know today that it's going to hit almost everybody. We will not have enough people to actually do the work that needs to be done. And, the government, being the government, does what it can to make the problem worse by not providing incentives to have children and by not providing incentives to work to make things worse. And so we already know today that 10 years, 15, 20, 30 years down the road, maybe the very biggest problem we will have in society will be a lack of people in the workforce. So labor might be the bottleneck. It might keep us from growing a company. It might keep us from being able to run a company at all, if you're not exceedingly attractive. Now think about all those companies that we have in Germany in the rural areas where, it's not particularly attractive to move to for people from outside. You will always find people who are willing to move to Munich or to perhaps even Berlin, even though I can't quite understand that. But we'll try to move somebody to some village, let's say Lower Main or something like this, or my hometown. Nobody moves here. So all those millions of companies that we have in those lost places where there isn't sufficient youth available that will stay there and is willing to work there, and there's nobody moving there. So clearly a lot of companies will not be able to survive in rural Germany. And that's the same is true for all other Western countries, by the way. It's not a German problem. It is a very accentuated problem that we have in Germany, but it also exists in other countries. First and foremost, for instance, Japan, Italy, and in the US, not to the same extent because they have a very large influx of young immigrants, young illegal immigrants from the southern border. Then one very important point about bottlenecks is the question, is it a static bottleneck or is it wandering? Because if it's a static bottleneck, well, then we can easily detect it and we can easily do something about it. And we will talk about bottleneck management measures in a short while. But if it's a dynamic bottleneck, if it moves around, for instance, depending on the product that we are currently producing, then it's, first of all, it's difficult to detect and it's very difficult to do something about it, right? And then we need to think about the options that we have. Sometimes the only option that we have is to increase physical capacity. Often enough, that's not necessarily the case. So, for instance, at the moment, we have the student project at a warehouse where the warehouse manager, or not, maybe not the warehouse manager, but the general manager of the company, they decided they need more warehouse space. So they built one more building because they thought they run out of space. Okay. Also, they want to spend millions on warehouse automation. They want to build a goods-to-person system. Okay, because they think they're not going to have enough people to do the picking for them. Now, when we looked at the warehouse, we identified a bunch of measures which they could implement to, first of all, shrink the warehouse space and make the people who work there more productive, so that with all likelihood, they neither need the additional building, nor do they need to spend any money on warehouse automation. They can work with the people they have if they just did what they did in a better way. So there are other measures than capacity increase in this case. And so the origin of the bottleneck, which they have, and they have two bottlenecks, one for static capacity, one for dynamic capacity. The bottlenecks were organizational and operational in origin. They were not physical, really. If you use the physical resources in a smarter way, the bottlenecks will not be active. And then we have things like, money, financial implications. So some bottlenecks hurt a lot because with every hour the system isn't operating, you lose a ton of money. This is, for instance, the case for automotive manufacturing plants. They cost millions when they stand still. And don't ask me how exactly these sums are calculated. I've heard numbers like 30 million euros per hour as cost for a standstill at the Daimler plant in Sindelfingen. Well, I don't know exactly why it cost money. I understand that it cost money because they're not earning money during that time. They're not producing cars which they sell. But that's an interesting question for a student paper. Anyway, I don't know anybody who actually has an answer to that question. But anyway, it's very likely expensive to have a standstill at an automotive plant. Sometimes a certain bottleneck might not even matter. So maybe it's just a feature that you can't offer at the moment, a feature that nobody wants anyway. So the financial implications differ quite a bit. And when you think about bottleneck management, you want to understand the financial implications of the bottleneck first so that you can select the appropriate measures. Now, there are different stages in the life cycle of a bottleneck or in the life cycle of bottleneck management. Now, a couple of years back, I was thinking about bottlenecks quite intensively, and basically that was all I was thinking about. And I came up with this structure. So when we think about bottlenecks, the first thing we may want to do in many cases is to prevent them from emerging in an unexpected place. As I mentioned before, there will always be a bottleneck. So you cannot prevent the existence of bottlenecks altogether. But you can prevent a bottleneck from emerging in an unexpected location sometimes, and you may want to prevent very particular bottlenecks. So for instance, you don't want bottlenecks because of supply shortages. That's a stupid bottleneck to have. If your customers don't buy, well, that's one thing. If your production is completely fully utilized, well, that's another thing. But if you don't receive some stupid part that you need for production and that's why you can't produce, well, you don't want that. So you want to prevent those bottlenecks. Another measure of bottleneck management is clearly identification. And I mentioned before that sometimes it's easy to identify the bottlenecks, sometimes it's not. I mean, if you don't receive supply from your suppliers, that's an obvious reason to have a bottleneck or to not be able to produce. So in that case, identification is fairly simple. However, if it's an internal bottleneck and if the bottleneck moves around depending on the product that you produce, maybe depending on the people who work there on a given day, then it's difficult to identify. Then the next thing would be bottleneck exploitation. And bottleneck exploitation is trying to get out of your bottleneck whatever you can out. So basically trying to remove all the organizational rules and the operational inefficiency that you may have at a bottleneck so that you're down to the complete physical capacity of the bottleneck. You fully exploit the physical capacity of the bottleneck. And if that doesn't work, or if that isn't sufficient, then we think about bottleneck elimination. So meaning you expand the physical capacity, right? But that shouldn't be the first step. That's the last step. So buying a second machine, buying a goods-to-person system, buying a second warehouse building, and so on, well, that's the last step, not the first step. But as I have described in my previous example about the student project, very often that's the first thing that companies think about. And then last but not least, because we have a bottleneck anyway in any system, we can think about bottleneck placement. So what is the machine, what's the production station in the system that has the lowest capacity? Because probably not all stations, not all resources have the same capacity. So one of them will have the lowest capacity, and we can choose that station very deliberately. And then we can protect that station with measures that I will explain next. But before I do, one of the very important things you need to realize about bottlenecks, and maybe you have already realized that, but I doubt that. Now, what does the existence of a bottleneck imply? Well, in our calculation examples, when we looked at the sandwich assembly line, for instance, or when we looked at the dentist, we identified the bottleneck as the station with the lowest capacity. So we used it to calculate the rate, because the inverse of the bottleneck process time is the rate at which a process can produce output. All right. So that means if the bottleneck becomes a little faster, then we can produce more. If the bottleneck becomes a little slower, we can produce less. And because the bottleneck is the station that determines the system throughput, we know, and that's a logical necessity, that an hour lost at the bottleneck is an hour lost for the whole system. So if you can't produce at the bottleneck for an hour, basically it means you could not produce at the entire system for an entire hour. So you lose that throughput, and you're never going to recover that throughput, right? So if you produce 24/7, or even just 2 shifts, or even just 1 shift, doesn't matter. But if you're not flexible, for instance, to work a little longer, in the moment you lose any throughput at the bottleneck, you lose throughput for the entire system that you will never be able to recover. So there's another implication that we can derive from that, and that is an hour saved at the bottleneck is merely a mirage. So it doesn't make a difference. You can be as efficient as you want at all the other process steps in the system, but they're not going to change the throughput of the system. The only thing that is going to change the throughput of the system is the throughput at the bottleneck. So you need to take care of the bottleneck first. Anything else doesn't matter. And I've seen this a lot, in systems where people expanded this capacity and they expanded that capacity and they spent millions on a goods to person system just to find out they don't even have enough truck gates to ship all the stuff that they have picked. So there's a lack of awareness of this point, but this is one of the most important points that you can take away from the book, The Goal, that all of you have read by now. Now, what does all of this imply for the management of bottlenecks? Let's think about this. So let's think about the prioritization of improvement measures. Let's think about the protection of the bottleneck. Let's think about maintenance, and let's think about batch sizes and single-minute exchange of die, and how lean in this particular case differs from the theory of constraints as it is introduced in The Goal. All right, so first, the prioritization of Kaizen measures, of improvement measures. Now, clearly, and this is really an obvious point, because the bottleneck is the element that limits the system throughput, you want to focus your improvement measures on the bottleneck, of course, right? So the improvement cycle of the theory of constraints that we will talk about in a couple of minutes, it really needs to be focused on the bottleneck. Any improvement in the system should first and foremost be focused on bottlenecks. But of course, we need to realize bottlenecks can move. And in the moment we have eliminated one bottleneck, what happens is that another bottleneck will emerge. Another station, another element of the system will become the new bottleneck. And so we shouldn't put blinders on and stupidly work on only one thing. But we need to focus our activities clearly. Then let's talk about bottleneck protection, because bottleneck protection is quite important. Now, we already established that the bottleneck is the element that limits system throughput beyond a certain threshold. So that means we must make sure that the bottleneck will always be able to produce whenever it needs to produce, right? Because, again, an hour lost at the bottleneck is an hour lost for the entire system. So one of the things that we need to take care of is that the bottleneck is protected. And one thing that means is that the bottleneck must never starve. What does starvation mean? Well, starvation in the production context means that a station runs out of parts to work on, even though there would be parts to work on. And that could be the case, for instance, because a preceding workstation has had a breakdown, or that somebody at the preceding workstation is not, for a brief moment, not working fast enough, or had to take a break, or whatever the case may be. A preceding production step cannot keep up for a short period of time. So one thing that we should do is we should have an inventory buffer just before the bottleneck. And now you remember we talked about this a lot. Inventory is evil in terms of lean. But, having a bottleneck starve is even more evil. So we want to make sure that the bottleneck never runs out of parts. So we keep a certain amount of safety inventory in front of the bottleneck station. And when the preceding workstation goes down or has some irregularity or faces whatever problem, then the bottleneck can continue to produce with parts that it takes from that inventory buffer, right? Because there will be variation in the production process, and we cannot eliminate all the sources of variation, so we have to deal with buffers to counter that variation, and an inventory buffer in front of the bottleneck station is one way of doing that. Now, it also means that the preceding workstation needs to have sufficient capacity in normal times to, on the one hand, serve the bottleneck station at the normal production rate, but also to fill up the inventory buffer again. Because if the bottleneck takes parts from the inventory buffer and the inventory buffer is depleted, it needs to be refilled. And it needs to be refilled while the bottleneck station is operating. So the preceding workstation basically has to have sufficient overcapacity to be able to do both, serve the bottleneck and simultaneously replenish the inventory buffer. So this is about bottleneck starvation. Never let the bottleneck starve. Another thing that we need to take care of is the blocking. We must ensure that the bottleneck is never blocked. So that what does blocking mean? And we saw this in the simulation model, in plant simulation. At some point, the subsequent workstation that had a higher process time variability built up such a long queue of inventory, such a long waiting line in front of it, that the previous workstation was blocked. It could not get rid of its parts that it processed. That's what is called blocking. And we need to make sure that a bottleneck station is never blocked. So whenever a bottleneck station works on something, it must be able to release it. And again, this means two things. So first of all, we should have an empty inventory buffer, free capacity, free storage capacity after the bottleneck. So the bottleneck has always physical space to get rid of the parts that it has worked on. And that's an obvious point. So to protect the bottleneck from starvation, you want to have a full inventory buffer in front of the bottleneck, and to prevent it from blocking, you want to have an empty inventory buffer after the bottleneck. Also, similar to the previous point, you want to make sure that the subsequent workstation has sufficient capacity to empty the inventory buffer after the bottleneck. So it needs to be able to process the parts that come from the bottleneck, as well as all the parts that are in the inventory buffer, because else the inventory buffer will remain full. And then when something goes wrong, the bottleneck will not be able to release its part. So starvation and blocking both are the results of variability and dependence. And that's important to understand. If there was no variability and dependence, so if the subsequent and the previous process steps, if they were 100% reliable and predictable, then we wouldn't have to have any buffers. But because that isn't the case, we need to have buffers. The next point about bottleneck protection is this: the bottleneck must never waste capacity. Now, what does that mean? One instance of wasting capacity at the bottleneck is if the bottleneck works on defective parts. Now, why would the bottleneck do this? Well, let's think about this. At some point in the production process, at least if you care about quality at all, you do have some quality checks. And, sometimes we have those quality checks directly before we pack items and then we ship them to customers, or we put them on storage to ship them to customers later. But by that time, the parts have already gone through all the production steps. Now imagine you produce a faulty part in a workstation, but you don't realize that the part is faulty. And then you bring that part to the bottleneck station. And then the bottleneck continues to work on that faulty part. And then later, just before packing or during packing, you realize, oh, that part is faulty. It's scrap. We have to throw it away. Well, that means that the bottleneck has worked on a part that is not going to be used. So effectively, you have wasted its capacity. Right? The bottleneck has wasted its capacity on parts that will be thrown away. So that means that the location of the quality check should be in front of the bottleneck. You want to check each and every part that goes into the bottleneck station before the bottleneck spends time and resources on those parts. A second implication is this. Any part that was processed by the bottleneck is very valuable. So you want to treat it very carefully. Imagine you process a part at the bottleneck and then you take it out of the bottleneck station and then you drop it and it breaks. Or you scratch it. Or you do something else to it that diminishes the quality of the part. So you can't use it for your customers. Well, again, the same thing happens that happened before. We've just wasted bottleneck capacity. So a part that was processed by the bottleneck station needs to be handled extremely carefully, because if that drops, that was capacity wasted for the entire plant, not just for the bottleneck station, but for the entire plant, because the bottleneck's capacity determines the process capacity or the system capacity of the entire plant. Another implication is this. Now, sometimes we can work on a part in the bottleneck station, but we could do the same. We could do the same work on a different station. Now, you may wonder, you may ask yourself, what's a realistic situation? Well, let me give you one example, not from manufacturing, but from an office environment, from engineering. So when you work in engineering, when you work for an engineering company, there are people who can do things that other people cannot do. You know, the very experienced, very talented engineers. And I mean, they have a limited amount of resources. So I can tell you from my life in the office, we had a guy in our team who was very experienced. He's been working for the company for more than 20 years. And he has seen and done a lot of things. And if we had a very complicated automated case picking project, he was the person to work on that. And so his resources, they were very valuable. Now, of course, he could also work on other projects. He could work on simple projects. But in the moment he works on simple projects that somebody else could have taken care of, we wasted his valuable capacity because he was the only person who could work on the complicated projects. And so that's the same, the same logic applies to senior management. So let's say, well, have you ever asked yourself why executives have an assistant? Or why people who can afford have somebody clean their house or take care of their garden? Of course, they could also clean their house themselves. Of course, an executive could take care of their travel expense reimbursement. They can also do, they can make photocopies, or they can send emails, they can organize meetings, they can book the flights themselves. Of course, they can do this themselves. They've done it when they were younger and less important. But somebody else can also do this. But at the same time, the executive can only, he's the only person who can make certain decisions that somebody else cannot do. So he can make decisions about merger and acquisitions. He can make decisions about certain contractual questions. He can make decisions about, HR questions that are very high level. But the assistant cannot. So the assistant takes away or processes a part of the workload that is on the executive's table, so that the executive can focus on all those parts that only he or she can work on. Right? So that's the logic behind it. And the last point here is the bottleneck should only work on actual customer orders. And this sounds so obvious that many students will dismiss this right off the bat, but it is not so obvious apparently to many companies. So I've had this situation. I was supervising a bachelor thesis at one of the local companies, one of the local manufacturing companies that all of you know. And they had a problem. They, at the same time, were having very high inventory of finished goods, and they had a problem with worker utilization in manufacturing, and they had a problem with long delays and late shipping to customers. So customers were complaining about late delivery. They ordered something and it took weeks until they received the produced parts. At the same time, they had a lot of inventory in finished goods. And so the task of the student was to find out what the heck is going on. How can it be that at the same time that we have a lot of inventory, we can't serve our customers? Well, it turned out that the people in production didn't work on customer orders, but they worked on parts that were convenient to work on. So it was much easier to work on something and put it on stock than to work on another part that is maybe more complicated to produce and ship it to customers. But that's the only thing that matters. The only thing that matters is customers. So you want to focus, of course, on customer orders. But a lot of companies don't do this. And it was so interesting to see this because there was this disconnect from the manufacturing world to the customer management. And, this happens all the time. People work on something that isn't actually the important stuff. They work on the non-broken part, so to speak. Now, the importance of bottlenecks also has implications for maintenance, of course. You want to make sure that your bottleneck station doesn't break down unexpectedly. So one thing that is always better than repairs is maintenance. If you maintain a machine properly, it is unlikely to break. If you change the oil of your car frequently, it's less likely to have an engine failure, right? So that is much cheaper. It's much cheaper to change the oil, and it's much more predictable when you change the oil than when you have an engine failure. And so that is one thing. So the other thing is that whenever you do service and maintenance, of course, you want to do this outside the normal operating hours. I mean, most systems do not work 24/7. So you could do service and maintenance on the weekend or during the night shift. And yes, that's expensive. It's more expensive than doing it during the day shift. But it's even more expensive to not be able to use the bottleneck capacity during the day shift. So I've seen a couple of systems that actually did work 24/7, except for a couple of days around Christmas. And so while everybody was celebrating Christmas, there was a bunch of people at the production plant taking care of the machines, doing the maintenance, so that the machines were ready for the next 12 months of operation. Now, the last point here is this. We talked about batch sizes and single-minute exchange of die. So I told you that in Lean, we have this ideal objective of having a batch size of 1. We want to have one piece flow because any batch size that is larger invariably creates waiting time. And so it increases the inventory. And as you know, inventory is evil. So Lean wants to have a batch size of 1 and basically wants to make as many changeovers between the different parts in production as possible. And that means we maximize the amount of tool changes in all the machines. There's a lot of tool changing going on in a Lean system. Now, in the theory of constraints agrees with that for the most part, but with one exception. You don't want to waste bottleneck capacity for non-productive activities. And that seems to make sense. So if you have a bottleneck, you don't want to have a batch size of 1 at the bottleneck because that means you have to stop production and change the tools. And even if the tool change is fast, you still have to spend some time on it, so it's not 0. And so you want to have a single-minute exchange of die at the bottleneck too, but not so often. So you maximize the capacity utilization at the bottleneck. You produce large batches at the bottleneck station. But at all other stations, this is where you can maximize the changeovers. This is where you break up the batches, right? And actually, it doesn't really matter because if you know where the bottleneck is and if the bottleneck is properly utilized, it does not matter that you waste some capacity at other stations that are not the bottleneck because they are not going to change the throughput anyway. Now, in the theory of constraints, as it is described in the goal, there's this 5-step improvement cycle. And you've read the book anyways, so we can go through this briefly. So the 5-step improvement cycle consists of identify, then decide how to exploit, then subordinate everything else, elevate, and repeat. So let's start with identify. Identify what is the system's constraint, what is the system's bottleneck, what is actually limiting the system throughput. And yes, obviously, you will say, well, yes, of course, we need to identify it first. I don't need to read the book for that. But it's actually not trivial. It's not so easy to identify the bottleneck. Now, in the past examples that we have used, we said the bottleneck is the station with the lowest capacity. But that is one way of looking at it. But maybe the capacity doesn't really matter. Maybe it's the capacity utilization that matters. So for instance, in the other book I'm recommending, in Factory Physics, they say, well, the bottleneck is the station with the highest long-term utilization. And that's not the same thing. You may have low capacity, but another station with higher capacity is actually more utilized because it breaks down all the time, and so you don't see this if you just look at the bottleneck capacity, right? So the bottleneck may be in a place that you don't expect, and you need to identify it first. There's a lot of literature on how to identify bottlenecks, a lot of scientific papers. The bottleneck may move around depending on the specific product that you currently work on, depending on the people who currently work in production. So it doesn't have to be a static position. And this is important to keep in mind. So then the next thing is, how do we exploit the bottleneck? And we basically just talked about that in the previous slides. We talked about the different measures for bottleneck protection and exploitation. So we want to get out whatever we can get out of the bottleneck in the best way. And so that point refers to the prioritization of improvement measures. It refers to the protection of the bottleneck. It refers to the maintenance, and it refers to batch sizes. Subordinate everything else. Now this one is related to the previous one. You subordinate all decisions regarding non-bottleneck resources to the bottleneck resources. This could, for instance, relate to maintenance scheduling, or to overtime, or to vacation planning. You had a machine breakdown upstream the bottleneck, where maybe you have to ask your staff to work overtime to make sure the bottleneck will have enough parts to process in the next couple of hours. So let me give you another example from the office environment. When you do your vacation planning, you want to make sure that your bottleneck resource person, the one who is most skilled at what he does and gets to work on all the complicated big projects, will not be sitting idle because some members of the team, some members of the project that whose input he depends on, have left for vacation. So sometimes that's difficult to plan, but you want to make sure that your most important resources are not idle, right? So you subordinate a lot of other decisions to make sure that he or she isn't idle. Now the next step is elevate. Now that we've talked about bottleneck exploitation before, which means we want to get the maximum throughput through the bottleneck, we can think about adding physical capacity. That's the elevation of the bottleneck. So it might mean that we add additional machines to the bottleneck workstation, or that we train bottleneck resources such that they can work faster. We can hire additional people. We can change the product such that its manufacturability is improved, and so on. And the result will be that if we do this properly, the bottleneck will stop being the bottleneck, possibly, and no longer limits the system throughput. But as you already know, there's always a bottleneck. So what happens after this bottleneck is elevated? Well, the next bottleneck emerges, and we need to go through the 5 steps, or through the 4 previous steps again. Every system has a bottleneck, always. And if we want to maximize the throughput in the system, we need to reiterate the cycle until the bottleneck is moving out of our internal system, for instance, to supply or to demand. And just as with lean, the idea is that your company, as you reduce the lead time and you improve the quality and you get better throughput, that your company will become more attractive to the market, and that the resources that you were able to free up due to lean and or theory of constraints improvements will soon be needed because the market will react to your improvement and you will experience higher demand. That is the idea.